Hello and welcome to this second part of Lesson 1 in Strength of Materials. My name is Hisham Saeed and welcome again to uh, this video. This video will learn about normal stresses, or some people call it axial stresses, and we'll learn about average normal stress, what does it mean, and what assumptions we're making in calculating it. And we'll see an example of calculating normal stresses along the length of a member with variable cross section. We seen in the previous part of this lesson definition of stresses in general, and we introduced the idea of three types of stresses: normal, shear, and bearing stresses. Here, normal stress is a force per area by the definition of a stress, but we're here careful about defining it as a perpendicular to the surface of my cut section. So we see here that if this is P, it's an axial force, and this is the cut area where I am trying to analyze the stress at. Sigma is equal to P divided by A. So like last part of this lesson, we explain here that we're trying to normalize the impact of this force by dividing it over the area. One thing we need to be careful here is that normal stresses don't get generated by only axial forces. So this is why I'm real careful about calling it axial stresses, because normal stress can be generated by an axial load or axial internal force and transverse load. So axial is easy, it's just force over the area, but transverse or anything that's not axial with the center line or the centroidal line of the member will cause bending. So that bending causes tension and compression at different parts of the section, like we'll see in a future lesson. But these tension and compressions are normal stresses. They are not uniformly distributed like we assume here in axial force, but they result into normal stresses. So just to understand this chart here, normal stress can be created by axial load or transverse load that causes bending, and then both of them at the end result in our what we call normal stress as a perpendicular stress to the cut section. So for this lesson, we'll focus on the stresses, normal stresses from axial loads. Also here, we're trying to clarify that the sigma, this normal stress we calculate, is assumed to be an average value over the cross section that we are analyzing for an axial load, under an axial load. Why is that? Because the distribution of stresses over the cross section here is not uniform. So at this section here, if we're analyzing the section closer to the force, we see that the more stresses kind of are generated along the center of the section where the force is applied. The deeper you go into the length of the member, the more uniform the stresses will be, but they're not that uniform. So a more accurate description here is for every little area of spot of your cross section, there is a little force, axial force, that is equal to the stress on that area times the little area dA or delta A. So a more accurate representation here is that this axial force P is the integration or the summation of these little forces, dFs, along the cross section that we are analyzing here. So let's see an example here. I'm trying to open my iPad. So the example we have here is a bar A, B, C, D with different cross-sectional areas and different forces along its length. So you see here my engineering paper, kind of virtual. So the first thing we do is we analyze the free body diagram or equilibrium of this member to figure out what are the internal forces we have. So taking out the member from its support. Once you take out the support, you reveal the reactions. This is a fixed support. So here we have AY, AX, and moment reaction MRA. The equilibrium equations here we apply are 3 because this is a two-dimensional problem. So if I apply some of the moments at A, nothing really happens here. All the forces are axial, so the moment reaction is equal to 0. And if I apply some forces in Y direction, I will see that AY is equal to 0. But when I apply some forces in X, all these axial forces, the net or the resultant will be opposite to the reaction I have. Now I assumed AX to be going positive direction of X, but I found here from equilibrium it's negative 200, so that negative is giving me a hint that the assumption I made about the direction is not correct. The value is correct, so what I have here is I correct the direction to be to the left. So the force here is going to the left. Your left. Maybe my camera here is showing you to the right. So it's to the left of the member. The thing here that we're trying to figure out is the maximum average normal stress. And to find that, we have to figure out what's the normal stress in every one of these different sections, cross-sectional areas. So we have here to analyze every one of these unique segments of the member because they experience different internal forces. We have different axial loads along the length, and also every segment has its own cross-sectional area. So sigma is equal to P over A or N over A. If N, the internal force, is different and the area is different, then there's a different sigma happening or occurring in this segment. So I have to analyze it and figure out now over the length of the whole member what's the maximum normal stresses. We can do that by two methods, like we learned in statics. The first one is cut sections, and the second one is force diagrams. As just an illustration of the first method, cut sections, we'll analyze only the first section of the first segment, AB. So if I cut through AB, I take out left free body diagram and the right one. I have the option of analyzing either one. I will analyze the left one, but before that I have to reveal here the internal force that happens or appears once I do that cut. So I'll analyze the left free body diagram, and it's a wise choice here because it's a very simple equilibrium, and I can figure out here that the internal force along the length of AB is 200 and it's in tension, which makes sense. The resultant of the 50, 150, and 300 is 200 trying to pull the bar out of the wall, so this is why the reaction is trying to pull it back in the wall. So this is just an example, but I want here to share with you the more efficient approach here, which is drawing an axial force diagram. Like we learned in statics, you start from the left, and once you start from the left, you set your positive direction for accumulating or adding the impact of each force you go over from left to right. So like we'll learn, if you're moving from the left here, start from the left, an arrow going to the left, this is a tension force. An arrow going to the right, this is a negative arrow compression force. So I start from the left, I hit the 200 reaction, so that will bring me up as 200. Nothing happens until B, so it's a straight line horizontal until I hit 300 here, and that's 300 is going in the negative direction, so it drops me from positive 200 to negative 100. And keep going with that, you will see that this is the diagram we have. You always hit 0 at the end. This is where you actually, it's a checkpoint for you. So if you don't hit 0, this means you messed up something here and along the length while you're drawing this diagram. So here I ended up with positive 500, and then I see here that this 50 pound is in negative direction. That brings me to the 0 point in the diagram. Now I can see here that every segment of this bar has different internal axial force. I call axial forces here N. So, but I can't clearly say which section has the largest stress. So this member here, NAB, um, is has the largest internal force. Let me see here 1 minute. Trying to use a point, but that's fine. So this member here has the largest AB, has the largest force, but also has the largest cross section. So I have to calculate the sigma internal normal stress for each segment and then compare them at the end. So sigma AB is equal to the force over the area, and you'll find it equal to 66.6 psi. PSI is short for pound per square inch, and this is the US units. In some problems, you'll be given in standard international units. Newton per meter square is the same as Pascal. And we can see here a conversion value between PSI and Pascal. So this is the first stress for the first segment AB. And then we can apply the same process for segment BC. We see here we apply the force over the area. The force should have the sign with it. So the force along BC is a compression force. So I included with negative, so I have here negative 50 psi. And this means it's a compression stress, compressive stress. CD, the stress there is also 50, but now that's a tension. So the question asks for the maximum average normal stress. If I just kind of ignore the signs, which is not correct generally, but for here it didn't specify the average maximum tension or compression, so it's just the absolute value. I can see here that the maximum stress happens along segment AB. So that's the end of the exercise here. We figure out what is required of the exercise. So we found the maximum stress to be at segment AB. So that's the end of this video. We learned about normal stresses, how they are generated by axial internal forces, and also transverse load that cause internal bending. We'll learn about the bending impact and its contribution to normal stresses in a later lesson. And we kind of went through an example of how to calculate normal stresses. So hopefully you enjoyed this part, and thank you for watching. Thank you. Bye.